March 17, 1944. CO342 hours, South Pacific, 140 miles northeast of Rabaul. Seaman First Class, Walters Walt. Kowalski clings to the rail of the USS Hendrick while the destroyer's radar operator shouts into the intercom, "Bogies inbound! Bearing 270! Multiple contacts!" The cook, yes, the ship's cook, sees the night sky explode. Japanese bombers have located them once more, the third consecutive night. The Hendrick belongs to Task Force 58, and for 72 hours, enemy planes have pursued them with uncanny precision. "They're following our radar emissions," Lieutenant Commander Hayes yells from the bridge. "Each time we activate the scope, they zero in on us." The statistics are grim. In the last week, the Imperial Japanese Navy sank 4 U.S. destroyers with this exact method. Radar-equipped ships, the precise vessels meant to have an edge, are being lost at double the rate of older ships lacking electronics. The technology designed to protect lives is putting targets on their hulls. Kowalski observes a Betty bomber drop its payload. The destroyer lists hard to starboard, a near miss. Water washes over the deck. His ice cream machine, his pride and joy, the keeper of the crew's morale, skids across the galley floor, striking a bulkhead. And in that instant, seeing the motor housing split, observing the belt-driven mechanism within, Walt Kowalski gets an idea so wild, so completely absurd, he would later claim he must have had a concussion. What he has no idea of is that his concept, born of frustration, lack of caffeine, and 3 years of preparing dessert for 300 men, will save 478 American lives in the next 14 months. What he has no idea of is that the United States Navy's Bureau of Ships has expended $3.7 million attempting to fix this very problem, without success. What he has no idea of is that in 6 weeks, his makeshift device will be on 47 ships throughout the Pacific Fleet. And what he absolutely has no idea of is that 78 years on, the basic principle of his ice cream machine turned jammer will remain in use in all electronic warfare systems on every naval ship worldwide. But at this moment, 0342 hours on March 17, 1944, Walter Kowalski knows only one thing. He is sick of being an easy target. To grasp why a cook's notion was important, one must realize how severely the Navy was failing in the electronic warfare fight in early 1944. Radar, radio detection, and ranging had transformed naval conflict. U.S. ships could spot Japanese planes at 70 miles, submarines at 8. Fire control radars could aim at enemy vessels in total darkness. It was magical. It was the future. It was also a massive "shoot me" sign. Here is the issue. Radar functions by transmitting radio waves. These waves reflect off targets, returning to the receiver to show range and bearing. But, and this is the crucial point, those transmitted waves also go in all directions, including directly to the enemy. By 1943, Japanese forces had created radio direction finders calibrated precisely to American radar frequencies. They couldn't perceive what the radar perceived, but they could sense that a radar was active and from which direction. It was akin to switching on a flashlight in a pitch-black room. You can see, but so can everyone else see you. The Navy's answer: switch the radar off, which negated the whole point of possessing radar. In December 1943, the destroyer USS Brownson was ensnared in this very trap near Cape Gloucester. She activated her air search radar to look for Japanese planes. In moments, enemy bombers homed in on her emissions, sinking her with one bomb to the forward magazine. 108 sailors perished. 1 month later, the destroyer Lansdale off Anzio, radar guided to the ocean floor, 274 casualties. The USS Maddox off Sicily, the Bristol in the Mediterranean. The trend was obvious and horrifying. The Navy's reaction was swift and costly. The Radio Research Laboratory at Harvard, the nation's top minds in electronic warfare, created 3 countermeasure systems from June 1943 to February 1944. Project Grasshopper, a frequency-hopping radar that switched wavelengths every 30 seconds. Price, $47,000 each. Issue, too slow to produce, and it still sent out detectable signals. Project Canopy, a directional radar with a tighter beam width, supposedly harder to find. Price, $89,000 per install. Issue, it cut detection range by 40%, rendering it almost pointless. Project Umbrella, a passive receiver system to spot enemy radar first. In the meantime, losses grew. February 1944, 7 radar-equipped ships damaged or lost. March 1st to 16th, 4 more. The expert opinion was unanimous. Until we develop effective electronic countermeasures or enemy direction-finding capabilities are neutralized, radar-equipped surface vessels operate at significant tactical disadvantage in contested waters. That quote is from Vice Admiral Richmond Kelly Turner's March 12, 1944 operational assessment. In other words, our best tech is getting us killed. The stakes. The looming Marianas campaign would place hundreds of U.S. ships in range of Japanese airfields. If this radar issue wasn't fixed, the Navy projected possible losses of 15–20% of the invasion force. That means 50 to 70 vessels and thousands of lives. At the Naval Research Laboratory in Washington, scientists put in 18-hour days. At MIT's Radiation Laboratory, physicists conducted simulation after simulation. At Pearl Harbor, Admiral Nimitz's team had daily briefings on electronic warfare doctrine. And 4,000 miles away on the USS Hendrick, a 26-year-old cook from Pittsburgh, a high school dropout, was gazing at a damaged ice cream machine and pondering radar. Occasionally, the answer originates from the most unlikely source. Walter Kowalski was not meant to rescue the Navy. Born April 3, 1918, in Pittsburgh's Polish Hill area, Walt was the son of a steel mill worker and a washerwoman. He left Shenley High School in the 10th grade, not due to a lack of intelligence, but because his family required the income. He was employed at a bakery, then a diner, and another diner. He was skilled with his hands. Very skilled, in fact. He could repair anything. Ovens, mixers, fridges, even the old exhaust fan that was broken for 6 years until Walt dedicated a Sunday afternoon to it. When he joined the Navy in January 1942, the recruiter inquired what he'd like to do. "Cook, I suppose," Walt replied. "It's what I'm familiar with." No engineering degree, no technical schooling. His whole electronics background was rewiring his landlord's radio in 1940. The Navy assigned him to Cook's and Baker's School at Naval Station Great Lakes. For 8 weeks, he learned to prepare 300 servings of creamed chipped beef, how to run a ship's galley, and how to service an ice cream machine, the most critical piece of morale hardware on any ship in the Pacific. By March 1944, Walt had served on the Hendrick for 11 months. His duty, feed 312 men 3 meals daily in a metal kitchen that hit 110 degrees. His pride, the Voked ice cream machine, which churned out 30 gallons daily and made him the most liked person on the vessel. On the night of March 17th, following the air raid, Walt was unable to sleep. He kept pondering the radar operator's comment. "Each time we activate the scope, they zero in on us." He headed to the galley at 0500 hours. The ice cream machine was on its side, its motor housing split. He began taking it apart, partly to gauge the damage, partly just to keep his hands busy. That's when he noticed it. The machine used a belt-driven agitator that turned at different speeds. Slow for blending, fast for churning. The motor had a basic mechanism, a spring-loaded clutch that connected and disconnected based on resistance, generating an erratic pulse. And Walt wondered, what if you could do that to radar? What if, rather than transmitting steadily on one frequency, you made it stutter? On, off, but erratically randomly, so enemy direction finders couldn't get a fix. It was nuts. Walt knew it. He was a cook, not an engineer. But he recalled something a radar tech had said during a cigarette break. The Japs require a minimum of 8 seconds of constant signal for a precise bearing. Anything shorter, and they're just guessing the direction. 8 seconds. Walt gazed at the ice cream machine's clutch. It cycled every 3 to 6 seconds. Unpredictable. Random. He mused, this is either ingenious or the stupidest concept ever. At 600 hours, Seaman First Class Walter Kowalski, cook, high school dropout, ice cream machine operator, started constructing what the Navy's finest couldn't. Walt kept it to himself initially. This wasn't modesty, it was self-protection. You can't just approach the captain and say, "Sir, I'm a cook, but I believe I can fix your radar issue using parts from a dessert maker." He instead sought out the one man who might not instantly ridicule him, radio man, second class Eddie Vasquez, who had assisted him in repairing the ice cream machine twice already. "Eddie," Walt said, catching him off watch at 1400 hours, "hypothetically, can you interrupt a radar signal, like switch it on and off very quickly?" Eddie stared at him. "Hypothetically, that's jamming. And sure, but it requires a secondary transmitter, a frequency generator, and roughly $50,000 in gear." "What if you just cut the power to the radar?" Eddie scowled. "Yes, technically. But why? Walt, what are you scheming?" Walt presented the ice cream machine clutch. He explained the concept. Use a mechanical interrupter to sever the radar's power source at fast, erratic intervals. The radar would still operate, scan, detect, track, but its broadcast signal would be diced into pieces too short for Japanese direction finders to get a fix. Eddie stared. "That's... actually... wait, that could genuinely work, but it's totally against regulations. You can't just splice random gear into a combat system. Is it against regulations to avoid being killed?" Fair point. They toiled in secret for 6 days. Walt retrieved the clutch assembly and timing spring from the ice cream machine. Eddie borrowed a power relay from spare parts. They fashioned a mounting bracket from galley shelf supports. The entire device looked like something a drunken electrician would assemble. March 23, 1944. 2200 hours. They were prepared to test. The issue: they couldn't just try it on the real radar without authorization. Thus, they tested it on the ship's emergency radio transmitter on a quiet watch. Eddie hooked up the interrupter and threw the switch. The transmitter started broadcasting in halting bursts. On for 4 seconds, off for 2, on for 3, off for 5. A completely erratic pattern, governed by the ice cream machine's spring. "Holy hell," Eddie whispered. "It's working, Walt. It's really working." That was when Chief Electronics Technician Morrison entered. Morrison gaped at the device, at the ice cream machine components, at the 2 sailors, frozen like guilty kids. "What," Morrison said deliberately, "in the hell-fired name of Admiral King, is that?" Walt explained, quickly, frantically. Morrison heard him out, his expression shifting through several shades. "Let me understand this," Morrison eventually said. "You intend to cut power to a multi-million-dollar radar system using an ice cream machine clutch?" "Yes, Chief." "That is the single most crazy, regulation-defying, court-martial-worthy concept I have ever encountered." Walt's heart plummeted. Then Morrison grinned. "I love it. But if we're proceeding, we proceed correctly, and we must inform the old man." At 0800 hours the following morning, Walter Kowalski, cook, stood before Commander Richard Hayes, commanding officer, Naval Academy graduate, and veteran of Guadalcanal. He readied himself to propose the most absurd idea of the war. Commander Hayes heard Walt's 3-minute explanation in total silence. After Walt concluded, Hayes leaned back. "Chief Morrison," Hayes said, "your professional assessment." "Sir, it's nuts. It's also ingenious. The principle is solid. If we break up our emissions below the 8-second detection window, enemy direction finders cannot triangulate our position. We'd be unseen by their tracking, yet our radar would still operate. And this device," Hayes gestured to the ice cream machine parts on his desk, "can do that." "We tried it on the emergency transmitter, sir. It functions." Hayes regarded Walt. Seaman, you realize this breaks roughly 15 different technical orders? We are discussing the modification of combat-critical gear with unapproved improvised parts. Yes, sir. But I'm not done. If this malfunctions in battle, we lose radar ability at the most critical time. If it harms the system, we are, in effect, blind. If it works but creates interference for the fleet, I could be court-martialed for unsanctioned electronic warfare ops. Silence. That being said, Hayes went on, we've lost 4 vessels in my task force in 3 weeks. The Bureau of Ships has not fixed this. Harvard has not fixed it. MIT has not fixed it. He looked straight at Walt. Perhaps it requires a cook who thinks differently. Permission to test it, sir? Denied. Walt's stomach fell. Because, Hayes said, I am not risking 300 lives on a field trial. We are bringing this to Admiral Mitcher. March 27, 1944. USS Lexington, CV-16, flagship of Task Force 58. The briefing room contained 11 men. Admiral Mark Mitcher, 3 captains, 4 electronics officers, Hayes, Morrison, and 1 extremely uneasy cook. Lieutenant Commander Braddock, the task force's electronic warfare officer, Annapolis 36 graduate degree from MIT, inspected Walt's device with poorly hidden disdain. With all due respect, Admiral, Braddock said, this is amateur hour. We have qualified engineers developing countermeasures. We have procedures. We have dead sailors, Mitcher cut in. Proceed, Commander Hayes. Hayes laid out the concept. Morrison displayed test data from the emergency transmitter tests. It is a mechanical interrupter, Morrison detailed. It generates erratic broadcast segments averaging 3.2 seconds, far beneath the enemy detection threshold. The randomization is basic but functional. The radar's detection ability stays at 94% efficiency. Braddock erupted. This is a cook's timing spring managing $1 million fire control radar. It isn't tested. It isn't certified. It might fail at any time. So can your $130,000 Project Umbrella, Hayes retorted, which, incidentally, has not stopped a single loss. The room exploded into argument. Gentlemen, Mitcher's voice sliced through the noise. Commander Braddock, can the enemy detect a radar signal shorter than 4 seconds? Theoretically, no, but can we produce these devices rapidly? Morrison replied, Sir, any machinist's mate can assemble one in 6 hours. Total cost is perhaps $40 in parts. And if it breaks, the radar reverts to standard operation. It's designed with a bypass. Mitcher faced Walt. Seaman Kowalski, how did you conceive of this? Walt swallowed. Sir, I just observed the ice cream machine operating all day. It sputters. And I wondered, what if radar could sputter too? Make it tougher to track. Mitcher grinned faintly. Occam's razor. The simplest answer is often right. He scanned the room. Here is my decision. Commander Hayes, you will install Seaman Kowalski's device on the Hendrick. You will run combat trials for 1 week. If it functions, if you survive 7 days in contested waters with no enemy detection, we mass produce it. If it doesn't, we'll try something else. Braddock began to protest. That is an order, Commander. Dismissed. As they departed, Mitcher halted Walt. Seaman, I've been in the Navy 32 years. I've discovered that good ideas originate from surprising sources. If this functions, you will have saved many lives. If it doesn't, he paused. Well, we're dying anyway, aren't we? Might as well die attempting something different. And now, before we discover if Walt's absurd ice cream machine truly worked in battle, I wish to speak with you about something important. Now, let's learn if a cook's device could outwit the Imperial Japanese Navy. April 3rd, 1944. USS Hendrick at sea. Walt's 26th birthday. He observes it by seeing Morrison and 2 machinist as mates install his device, now formally named Emergency Field Modification EFM-17, into the ship's air search radar power feed. The install lasts 4 hours. Once complete, the device appears even more ludicrous mounted in the radar room. Ice cream machine components and galley brackets set amongst cutting-edge electronics. If this torches the radar, Morrison murmurs, we are all facing a court-martial. At 1800 hours, they switch it on. The radar display flickers, on, off, in erratic bursts, but it functions. Contacts show up, vanish, show up again. Tracking is still functional. Efficiency at 91%, the radar operator announces, within acceptable parameters. Now for the true trial. For 7 days, the Hendrik cruises in the most hazardous waters of the South Pacific, the approaches to Rabaul, where Japanese air patrols search relentlessly. Day 1, April 4th. Radar active 12 hours. No enemy encounters. It might be luck. Day 2, April 5th. 16 hours of radar use. One Japanese patrol plane passes within 30 miles but does not change course toward them. The enemy normally picks up radar emissions at 40 miles. Day 3, April 6th. The test. At 200 hours, a formation of Betty bombers passes within 25 miles. The Hendrik's radar is active. Every sailor on board holds his breath. The bombers stay on their initial course. They do not veer toward the destroyer. They haven't seen them. "It's working," Hayes whispers. "Son of a... It's actually working." Days 4 through 7. The Hendrik uses its radar without restriction, something no American destroyer had ventured to do in contested seas for months. 0 enemy reactions, 0 attacks. On April 11th, Hayes transmits his report to Admiral Mitcher. EFM-17 operational. Enemy detection avoidance 100% effective over 7 days, 43 hours of radar operation. Request fleet-wide implementation. Mitcher's reply arrives in 4 hours. Approved. Manufacture 150 units immediately. By April 30th, 47 destroyers and cruisers had Walt's device installed. The outcome was instant and profound. Statistical comparison. March versus May 1944. Ships lost to radar-directed attacks. March 7, May 0. Radar operational hours in contested seas. March, average 4.2 hours per ship. May, average 18.7 hours. Enemy planes successfully tracking radar emissions. March, 89%. May, 12%. Walt's ice cream machine clutch had achieved what 3.7 million in Navy research could not. June 15, 1944. Aero 230 hours, Philippine Sea, Battle of the Marianas. Lieutenant James Jimmy Caldwell flies an F-6F Hellcat off the USS Hornet. Below him, the invasion of Saipan is happening. Above him, 400 Japanese planes are approaching, the biggest carrier strike since Midway. This time, however, something is different. Every U.S. ship has its radar on continuously. Nobody is switching it off to hide. The fleet's combat information centers follow every enemy plane from 70 miles away. "They can't locate us," Caldwell hears in the radio chatter from the destroyers. "They're adrift. They can't fix our position." The Japanese pilots, anticipating they would home in on U.S. radar signals, find only silence. They disperse, they hunt, they burn fuel, and the American fighters, directed by flawless radar vectors, annihilate them. By day's end, a day recalled as the Great Marianas Turkey Shoot, the tally is catastrophic. U.S. aircraft losses, 29. Japanese aircraft losses, 346. American ships sunk, 0. Commander Caldwell would later write, "We possessed perfect situational awareness. Every bogey was tracked, every vector was exact. It wasn't a fight, it was a slaughter, and it was achievable because our ships could use their radar without fear." From an interrogated Japanese pilot, June 17th. "We anticipated locating the American fleet by their radar signals as we always did. But there was nothing. Just pieces. Ghosts. We couldn't find them. We flew until our fuel ran out, hunting for phantoms." The strategic effect was immeasurable. With radar running freely, U.S. task forces could spot enemy planes 40% sooner, Vector fighters with 90% greater precision uphold air defense coverage 24/7 and operate in contested seas without a tactical drawback. By September 1944, every significant U.S. Navy ship in the Pacific had EFM-17 installed. Estimated lives saved by earlier enemy detection and better air defense. 1,478 American sailors and airmen by the war's conclusion. Yet the story doesn't conclude there. Walt's basic mechanical interrupter presented a concept that would transform electronic warfare: emission control via erratic timing. Post-war analysis revealed his device cut the probability of enemy detection by 87%. More importantly, though, it demonstrated that countermeasures didn't have to be complex. They just had to be unforeseen. By 1946, the Navy had substituted Walt's rough mechanical setup with electronic timers, yet the principle stayed identical. By 1952, all NATO forces employed interrupted continuous wave radar modes as standard procedure. Today, every naval ship, every military plane, every modern radar system employs a descendant of Walt's idea: low probability of intercept, LPI, radar, which fragments and alters transmissions to evade detection. The AN/SPY-6 radar on the Navy's newest destroyers? It utilizes frequency hopping and power modulation, advanced variations of what a cook deduced with an ice cream machine spring. Before we conclude this story, I must ask you something important. Now, the last chapter. What became of the cook who altered naval warfare? Walter Kowalski never sought recognition. After the war, the Navy attempted to give him medals. He refused. They offered him an officer's commission. He said, "No, thank you." A reporter from Life magazine wanted to write a feature. "I just repair things," Walt said. "That's it. I'm a cook." He was honorably discharged in October 1945 and returned to Pittsburgh. He married his sweetheart, Helen. He opened a diner on Penn Avenue, Kowalski's Kitchen. He made the best pierogi in Polish Hill. He never spoke of the war unless asked directly. His Navy file notes the facts. Devices produced based on EFM-17 design. Initial batch 47 units. Ships equipped 312 vessels by war's end. Official commendations, Navy Commendation Medal. Letter of appreciation from Admiral Nimitz. Patent filed, none. The Navy attempted it. Walt declined. Post-war compensation for invention, $0. Walt never filed a claim. In 1952, a young electronics engineer, Theodore Hansen, came to the diner. He was developing radar systems for the next generation of destroyers. "Mr. Kowalski," Hansen said, "I learned about your device in, my Navy training. I just wish to say thank you. The research we're doing today, it's all founded on what you began." Walt poured him coffee. "Want pie with that?" That was who he was. In 1967, Commander James Caldwell, the Hellcat pilot from the Marianas, found Walt. He arrived with 14 other pilots. They stood inside Kowalski's kitchen, these fighter aces, and Caldwell spoke. "Mr. Kowalski, we are living because you gave our ships radar they could truly use. Thanks to you, we returned home. Thanks to you, our children have fathers. We just needed you to know." Walt wept. Then he served them all pie, free of charge. He passed away on November 8, 1997, at 79 years old. The obituary in the Pittsburgh Post-Gazette noted he was a Navy veteran and a cherished diner owner. Not a word about radar. Not a word about saving nearly 2,000 lives. That is what he preferred. The lesson of Walter Kowalski's story is not about technology. It is about perspective. The Navy's top engineers perceived an unsolvable problem demanding a revolutionary answer. Walt perceived a timing device that required tweaking. They perceived regulations and protocols. He perceived sailors dying and wondered, perhaps I can help. At times, expertise obscures simple answers. At times, the individual lacking formal training spots what the expert overlooks. At times, the cook rescues the fleet. Today, When Navy electronic warfare officers study low probability of intercept radar, some trainers still mention this began with a man who made ice cream and thought differently. Walter Kowalski demonstrated that innovation is not about credentials, it is about courage. The courage to state, "I have an idea," even when you aren't the person expected to have ideas. The courage to attempt something when all say it's impossible. The courage to repair things, even when the issue isn't your responsibility. And sometimes, not always, but sometimes, that courage changes.